I'm Shai. This is a joint work with Chris Parker, who was an American when we submitted it, but now it's Virginia. Please ask me any questions during the talk. I would rather everyone understand everything than I get to finish all the slides. I don't think that's as important. I prefer everyone to understand everything that I will talk about. Okay, so it talks about ex post equilibrium market recommendations. And the model is pretty simple. So the model is kind of a congestion game, but with limited information. So you have agents who choose a market, and the payoff at each market depends on the other player's choices. Kind of standard in a congestion game. And the utility, so the sigma is a strategy profile. And this is a little imprecise, but a little informal. But the utility for certain strategy profiles, so for certain choices of agents and markets, is just going to be, their volume times the price at the market, and the price is kind of a function of where exactly the agents go, minus their distance or the cost of traveling from where they are, from where their home base is to the market. And the price is basically straightforward as well. It's just the market size times the sum of the volumes of the agents at J. That's a bit informal, but I thought that would be the clearest way to show it, to the power of some market elasticity. So if you think about if beta is 0, then the price doesn't depend on any of the other agents' actions. It's always just alpha J, and beta is going to be negative. So typically you could think of beta as -1. So it's just going to be alpha J divided by the sum of the other agents' utility. And typically it's going to be between 0 and -1. Make sense? Okay, so yeah, so basically more agents at the market, price goes down, utility goes down. And our main motivation for this is farmers in India. Farmers typically are single product farmers. They just farm potatoes or onions or grapes, and they have to choose which market to go to, and they kind of face this trade-off. Should I go to a bigger market? How can I expect more sellers at? But maybe it's further away, and then I don't know where the other people are going to be, and I don't know what yesterday's prices are like, and they only go. Typically, they only sell their produce at the markets just a handful of times every year. So these decisions are life or death decisions. They're crucial decisions, and literally a lot of farmers commit suicide because they don't make enough money. So this is really a crucial problem. And there's some other motivating examples. If you think about Uber drivers, so say you're an Uber driver over there near Marion. This is in Indiana. It's a state, you probably never heard of it. It's a state south of Illinois. And if you're over here, this works. If you're over near Marion, you wake up in the morning and you kind of have to decide, where do I want to start my shift today? So you could just wait for rides to come up organically, but they're probably not going to get that many rides over there. So you could just drive to Marion, or you could decide, you know what, I'm going to drive like an hour and a half to Indianapolis, and there I'll get more rides. But immediately you can see the problem. If all the Uber drivers wake up in the morning and all of them go to Indianapolis, they would have been better off, this guy would have been better off going to a nearer town. And then another motivation is a polling location. So you want to go to poll, and you don't know how many other people are going to be there. There's going to be different queue lengths at different places. So what makes it so hard to make good decisions here? First of all, there's just a lack of information in many of these, right? So typically these farmers, at least years ago, 10, 15 years ago, they didn't even know what the prices were, previous day's prices were. And Uber driver wakes up in the morning, they don't know what the supply, the demand is going to be like in Indianapolis and any other city. And similarly, you don't know what the queue length is. Another kind of problem that creeps in is that even if you're provided this information, maybe you don't really trust them, right? So in India, farmers, it's well known that there's lack of trust in the government. And even an Uber driver, Uber tells them, hey, maybe you should go here. It's like, should I though? Should I trust them? And another, the main problem may be is strategic behavior. So you don't know what the other agents are going to do. And you must commit to a strategy before learning the other strategies. So if you think about the farmers, they need to drive, and sometimes they drive 100 miles to a market. So you drive 100 miles to a market, you can't go back. Right? You've wasted your whole day. Similarly, an Uber driver goes to Indianapolis, he's probably not going to say, you know what, I'm just going to go back. Right? I'm going to go drive an hour and a half back. Problem clear? All right, so one thing that was done is trying to provide more information. And this actually did help. So in India, there's a paper by my co-author, and they showed that just providing people with yesterday's prices actually reduced price dispersion. So overall, it was pretty good. But sometimes information actually is bad. And we can see this in this very simple example. So here, the prices are, beta is -1. So basically, as simplest example is if seller 1 goes to market A and seller 2 goes to market B, seller 1 gets, so the price at market A is going to be 90 divided by 10, which is 9. He's going to make 10 times 9, which is 90, minus the cost to travel there. So that's 30. So he's going to make, I don't know how to make it point. Oh, there it is. This is trickier than I thought. Okay. So he's going to get 60 if seller 1 goes to A and seller 2 goes to B, and so on. You can see that sometimes if they make a really bad decision, they could actually have negative utility. And then you can think about what happens. Okay, so if we give them information and we kind of play, so we look at a 2-shot game, but I think it's helpful to think of this as a many-shot game for purposes of this. Say they both go to market A on the first day. And then they get the information, right? So they get the information, everyone was at market A, then they both make the rational decision. The next day, they both go to market B, and then they're screwed again. Then the next day, they have all the information. They again choose to go to market A. And you might think, yeah, this probably doesn't happen in real life, but it turns out that it kind of does. So our solution to this problem is basically just to recommend an ex-post equilibrium. So a pure Nash equilibrium. And importantly, ex-post means that they don't regret their decision, right? So, and especially when you couple this with information. So you tell them, hey, you should go to this market. They go to that market. Then the next day they see the prices of the markets and they think, yeah, you know what, I couldn't have done better, right? So that's the main idea. And the advantages, so first of all, there's this immediate advantage. If it's an equilibrium, no one can do better. Importantly, no one can do better, but it also increases this trust because it's verifiably good, right? So you can check the information, you see, yeah, I couldn't have done better. Next day you get a recommendation, you follow it, you see it was a good recommendation, and this kind of creates trust. And intuitively, this is going to lead to low price dispersion because you're going to be, allocating agents more efficiently or more correctly. And it looks like there could be a possible welfare gain, especially if you think about the simple example, right? If you tell them just go to different markets, already they're doing better than if they went to the same market. But if we go back, you can kind of see, yeah, but one of them is strictly better than the other for A, one of them is better than the other for B. So maybe it's not optimal. So that's one of the disadvantages is that you're probably not getting, you're probably not getting optimal welfare. Another disadvantage or problem is that a Nash equilibrium might not even exist. How do we know a Nash equilibrium exists? So if we want to recommend one has to exist. And another problem is that this kind of hinges on everybody following this. So if some people start not following the recommendations, what goes on? Now, one thing I want to stress is that the main advantages really only happen, so the first two advantages really only happen when it's a pure equilibrium. So you might think, oh, I'll just recommend a mixed strategy or a correlated equilibrium. Right? So mixed strategy equilibrium guaranteed to exist. We're good. But then it doesn't have these nice properties. It's mixed strategy. There's some realization. Maybe this isn't the best response anymore. Right? So ideally, we'd really like to recommend pure equilibrium.
How does it eliminate negative welfare?
Oh, so okay, it eliminates negative welfare because you can tell, first of all, you can tell someone just stay home. And you give them their actual best response. So there's no one's going to have a negative welfare. Right? You're not going to have the situation where someone travels to a market, gets a low price, and his travel cost offsets that.
So this is with the presumption that everybody will follow the recommendation.
Yeah. If everyone follows the recommendation, this eliminates negative welfare. So some of the research questions we have here, there's a bunch of them. The first one is just does a pure national equilibrium even exist? And then we want to ask, is there a significant welfare gain for the farmers? Is there improvement in price dispersion? There's a bunch of questions we can ask. How suboptimal is this? And going to your question is, how much does this actually depend on people following the recommendations? So, and there's a bunch of other questions that we ask and are interesting, but I'm not going to get into all of them here. One thing here is I say, is there a significant welfare gain? And the question is, relative to what? Relative to the optimal? Of course not. Relative to what they do. And ideally, we'd like to know what they do in practice. But what is the benchmark? What are we actually comparing against? So first I'll look at the first question, then I'll get to the second question. So the first question is, does the pure Nash equilibrium always exist? And the answer is no. A pure equilibrium might not actually exist. So already out the bat, we're done. We can't necessarily recommend a pure equilibrium. So what are we even doing here? But it turns out that there always is one. Like empirically, when you check it, it's impossible to find a case, a setting where there isn't one, unless you engineer one for the counterexample. And we show that there's an equilibrium in the large. Under certain mild market concentration, basically you can think about, if I take that example, put it to one side, then I make a big market here, there's still no equilibrium. And so under these mild assumptions, which are necessary just from this example. And basically what this means is, for any epsilon, if the economy is large enough, there's a strategy profile that no one can deviate by and improve by one epsilon, so kind of standard. And the nice thing is the proof is constructive. So we basically give an algorithm for finding this equilibrium, if it always exists in this case, or this almost equilibrium. And now the second question is, okay, what do we compare it to? So we want to know how farmers actually choose their markets, but it's really hard to figure out. So we actually did a survey of 500 onion and potato farmers in India. And we asked them questions like, how many other farmers do you talk to when deciding when to sell your produce? How do you choose which market to sell? Where is your nearest market? Do farmers close to you generally go to the same market as you? And so on. There's a bunch of questions. You can read them in the paper. And we got a summary, but the thing I want to focus on is this, which is, do farmers close to you generally go to the same market as you do? And we get an overwhelming yes. So 89% of the farmers basically say, yeah, I go where I go, all of my neighbors go, right? So intuitively, we actually get this problem that we saw in the simple example where everyone's going to the same place. Which is going to cause what I'm looking for, suboptimal. It's going to cause suboptimal prices and suboptimal wealth. So we want to compare to the strategies and how do we get, so we got some reasonable strategies that we think, I'll talk about them in a second, from the survey. And then we compared them using parameterized data from Indian agriculture. So this is a different data collection that we did that was actually done by my co-author, and also using synthetic data. So this kind of gives a proof of concept. And the synthetic data allows us to do all these comparative statics and to check things about like what would happen if there was lower market penetration and things like that. And to quantify the advantages, we compared to four farmer strategies. So the first one is travel to the nearest market, which sounds extremely naive, but it turns out that a lot of farmers actually use this strategy. So a lot of farmers just travel to the nearest market, no matter what happens, even if they find out that the prices, they don't even look at the prices. So even if they found out that the price in another market that's not nearest is better and they would get better welfare, they still do that. And the next one is kind of another naive one, but it takes into account the market size. So travel to the highest welfare market if you don't know really anything interesting about what the other farmers are doing. So one way you look at it is just say, okay, all the other sellers stay at home. You get the same results if you say, if you take arbitrary amounts at different markets. But this is the easiest way to explain it. Another one, which is kind of natural, which is what you would think, which is what maybe you might come up, or I would come up with, is look at the prices that there were yesterday in some sense, and just best respond to it. Which this is one of the strategies that we believe they actually use, right? So they say that they use a strategy, but the problem is they simultaneously best respond, right? So everyone gets the same prices, the same information, and then they all best respond. And the last thing we checked is, okay, so if we do this once, if we simultaneously best respond, that's nice, but what happens if we iterative best response? So this kind of sounds like it's an algorithm for computing an equilibrium maybe, but it turns out that we just get into cycles. Right? So it turns out that this is pretty bad. Every instance we ran this on, this just runs into cycles. And you can think about the simple example where they go to A, they go to B, they go to A, they go to B, they go to A, and so on. And we looked at a bunch of different metrics. The ratio, the percentage of the sellers that are better off under our recommendation, what is the percentage improvement conditioned on improving, price, coefficient of variation, HHI index, or HH index. How many of them are regretful if they use the original strategy, and a bunch of other things. And last one is, how many of these other strategies actually end up in equilibrium? So that kind of ties into how many of them are regretful. And just a taste of it, this is results using the data on a crop called produce called grape samani, which I don't actually still know what it is, but it's a type of grape. And just pick your own, pick a column, just say best response. If you look at best response, welfare ratio 3 times better. 94% of the farmers are better off under our recommendations. Improved by a lot. Coefficient of like the prices dispersion is increased, and under the best response strategy, a lot of them are regretful, and none of the simulations came up with an organic equilibrium. Get similar results from synthetic data. One interesting thing that I was actually surprised is the robustness we have to market penetration. So even when the market penetration is like 25%, don't worry about the 0, 1, 2, 3. Even if the market penetration is about 25%, and there's a lot of uncertainty about other agents' volumes, the agents that are given recommendations actually do really well, right? So they get almost all the welfare that they expected to get from the recommendation. And that's pretty much it. So we don't really have a lot of data at the farmer level. So this was done using a bunch of different data sets, but it would be nice if we actually knew what the farmers, so we don't actually know what the farmers are doing. We don't know this farmer went to this market today, this farmer went to this market. It would be nice if we could get that and actually do a comparison. And there's a subtlety, which is there's aggregators. We don't have that much data. We don't have any data above them. But one thing we kind of figured out is the travel costs are actually prohibitive. So it was surprising, but the travel costs are high. So these are really small farmers. They produce very small amount of onions or potatoes or whatever it is, and a lot of their revenue actually is spent up in the travel costs. And finally, we're only considering here, like I said, a one-shot game, which is relevant for very perishable goods. But it's interesting to kind of look at what would happen if we had, if farmers could choose which day they would go to a market. What could we recommend? Okay, that's it. Thank you.